Okay, can you guys see the slides?
Yes, sir. It is visible.
Okay, great. So I think we can start it, okay?
Yes, sir. Yes.
Okay, great. So as we discussed last night, right? Night and last night, probably you guys tomorrow, yesterday morning. This is the Gillerite function theory for heterojunction. So heterojunction basically, follow almost similar, like lesions with homojunction. The difference will be what? The difference, the offset of conduction band and valence band. See this delta E, delta EC or delta EV. This, example for this case, for the whole transport, for the whole, transport at the junction, barriers reduce, right? And then for electron transport, you think about from N to P, now it gets more difficult, okay? That can be seen from what? From these functions, right? Current, then the dP basically means diffusion current, EMS basically means what? The emission current, okay? Then you can see that delta EC or delta EV will impact that a lot, especially the depletion. So with that, you can compare, which one is more, dominant, and then you simplify that equation that either VDP or VEMS, okay? So V here, you can simply consider that either can be, that's probably the, not the velocity, it's more like, the probability, okay? So that's just a general equation here for the, heterojunctions. Okay, with that, I think now let's talk about a few examples, okay? A few examples here. What are the real solar cells that take the heterojunctions, right? You can see clearly, any junction where the band gap is different, when you have P and N have different band gap, then that will be the heterojunction. That's why amorphous silicon solar cells heterojunction, containerized heterojunction, CIGS is also. First, let's take a look at this amorphous silicon. The amorphous silicon solar cells, what you can see here, basically the PIN structure, okay? This is the PIN, okay? Then PIN. And then what is the P, that is the P, basically you see is alpha, that's amorphous silicon P layer, and then amorphous silicon I layer, and then amorphous silicon N layer, okay? And then typically, above that, you have the TCO, and then you have what? You have the metal substrate, okay? Metal substrate. So one of these, if you think about amorphous silicon solar cells, so you can see this have to work. Right? You have the substrate here. This is substrate. And on top of substrate, you basically deposit this I amorphous or P amorphous, N P amorphous, and then you have this TCO transparent conductor. The sunlight come from the bottom right here. Sunlight come from the top. So basically, you look at here, the sunlight from the top. But when you look at the solar cells here, it's kind of reflected by 180 degrees, right? That's why the substrate is sunlight come from the top, you reflect it back. So that's then since the metal is on the top, right? Touch the top electrode touch the bottom electrode. That what does that mean? That means the solar cells are collected in series collection. So here, if you assume that there's a single junction of amorphous silicon solar cells, has a maximum power points. At that position, the voltage is 0.8, then current is 15 milliampere per centimeter square. Then you will need, if you collect these solar cells in series, basically, you can find out if you have, if the active areas is, is 100, right? What does that mean? If you want to get, the output of the solar panel is 100 milliampere, right? And each of solar cell is 15, right? Basically, if you collect that, if you collect this, right, this one is parallel, okay. This is the series, and then this is not, right? So that should be the parallel, right? So this should be parallel, okay? Parallel, okay. This should be parallel because if you consider the area, right? Each of the solar cells have like 15 milliampere per centimeter square. If you want to get, the total, 100 milliampere, and then you need to collect this, this about 6.67 centimeters solar cells in parallel, right? And then in parallel, you know that current will be add together, right? Current add together, okay? If the series, the voltage add together, so this should be in parallel, okay? What does it mean here? So here, if you look at this PIN amorphous silicon solar cells, why you call that amorphous? Even you have p-type amorphous, I-type of I amorphous, and then n-type amorphous. So the reason is that typically if you look at this on this p plus side, that typically you most of the time you do not use p-type p-type amorphous. You basically use something called silicon carbide. Okay, silicon carbide, and then silicon carbide there is what you call that window layers. Okay, window layers that basically it means it has 1.8 to 2.2 EV, right? So the amorphous silicon solar cells, their band gap is about 1.7 to 1.8. Okay, 1.7, 1.8 EV. Now since the P plus has the band gap about somewhere above 1.8, and then you see the band gap is different, right? Now your phone junction is this I, this is P plus, that P plus I, will be what? A different junction. That junction called heterojunction because their band gap is different. Okay. So typically, if you look at this one, so basically you can see this what feminine, right? Feminine, okay. Feminine is aligned, right? This is the right. See here, this feminine is close to the valence band. You call it P plus. This feminine is close to N plus or N plus. You call this what? N, right? So that's the PIN. We can P plus I N plus. Okay, so that's what you see there. And then, as we discussed before, if you have these PIN structures, what you see there, right? The feminine will be aligned, but in the I layer, the potential or the electric field will be pretty uniform, right? Pretty uniform. Okay, that's basically equal to VBI divided by the distance or thickness of that I layer. You get that electric field. Okay. So here is a question, basically, ask you. Now, why is this larger band gap silicon carbide window layer was used instead of P plus amorphous silicon used in typical amorphous silicon solar cells? So actually, if you read this question, probably you know that the the P plus amorphous, right? Even it's very thin. You know that amorphous silicon is different from crystalline silicon, right? Crystalline silicon is indirect bandgap materials. So absorption coefficient for crystalline silicon is pretty low. That's why you use very thick layer, like 400 micrometers thick. Like crystalline silicon, either N-type or P-type, absorbs the sunlight. But amorphous silicon is different. Amorphous silicon has very high absorption coefficient because amorphous silicon is direct bandgap materials. Okay, so even it's very thin, like 10 nanometers, it absorbs a lot of sunlight. Okay, then if that absorbs a lot of sunlight, it's heavily doped. It's actually the mobility pretty low. A lot of heavily doped. That means you have a lot of defect there, right? A lot of defect, you will decrease that charge transport, and then that blue light response will be poor. Okay. In order for that not to happen, you want to use a larger bandgap so that the blue light or this sunlight will not be absorbed by the P plus layer. Okay, that's one reason, right? One reason, okay? Another reason, You may think, I can still use P plus amorphous silicon, but I use, uh, very thin, right? I use very thin there, like what, 5 nanometers. I may not absorb a lot of sunlight. And then that cause problem, you remember here, you still form a PNI junctions, right? PNI junctions. When you form the junctions, what does the junction do? The junction form building potential, right? Because in the junction there are building potentials there. That building potential will sweep over the charge away, right? In order for the junction provide sufficient electric field, the junction should be thick enough to form that building potential, right? That means if you cannot just make P plus very thin, should be have a certain thickness, okay? That's what does that mean, right? So with that certain thickness, the light absorber will be even stronger because it is direct band gap semiconductor. Okay? And then the other reason you can, so B is also the reason, right? And then C will be amorphous silicon, carbide has a larger band gap than the P plus. That's not amorphous. That's more like silicon carbide. Silicon carbide has a large, amorphous. The larger band gap than P plus. So as I just mentioned, because the band gap is higher, is pass through more light goes to the I amorphous silicon. So that C is also right. So that's why ABC is right. The answer here is D. Okay, here's D. That's about amorphous silicon. I think we understand what's going on with amorphous silicon. Okay, class is silicon carbide, so that's why the band gap is larger than the amorphous silicon. That's why it's called heterojunction. Okay, and then another type of solid cells is also heterojunction is cadmium telluride. Okay, cadmium telluride. So cadmium telluride, itself, its band gap is 1.5 eV here. Then that's the typically, you can see that's a P, is P layer, and then N layer is here. Okay, N layer is there. This is a N layer. The band gap is 2.42 eV. Okay, 2.42 eV. Now you see the cadmium telluride and then cadmium sulfide for the junctions. Then this is the cadmium sulfide because the band gap is what? It's 0.42 right here. 0.42 eV. Here the cadmium, telluride is that 1.5. Okay, 1.5 eV. This 1.5 is the band gap difference. That's at this region you form what? Heterojunction. Okay, basically because their band gap is different. Their band gap different, their Newman HOMO will not be continuous, right? At that interface, right? That interface either you add the delta EC or either reduce delta EC. Depends what the band structure look like. So typically, you want your if you draw these band structures, you want the band structure happen something like that. Why is that? Because think about, you have sunlight comes, you generate electron, right? And then this part is what? N, right? This is P, right? This is P. Basically, the band structure inside, will move the electron to here. And then the junction here swap, just swap the electron to the left side, right? And then the hole, will go to the other side, okay? That's why, you want that junction, the building potential or the bending happens like this. You don't want to go opposite, right? You don't want to see I have my, okay, I have my light absorption happen here, then I generate electrons. I want my electron go all the way down, and then my holes also go all the electron go all the way up. That is a lot energetic variable. The holes go always down. It's more difficult, right? So that's what it means. Okay, that's why the band structures happen like this. Okay, happen like this. The electron goes left, the hole goes right. Okay. So with that, there's another common heterojunction. It's called CIGS. I mean CIGS. I'm not sure now. A few years ago, 10 years ago, it was very hot. Very hot technologies. A lot of companies try to customize. This is also polycrystalline. If you look at this, see polycrystalline, right? Or big crystals, right? A lot of big crystals. Big crystals. This is polycrystalline, okay? Polycrystalline, because you have a lot of the grains. So you have a lot of grains, inside the structures. The different from silicon, you have, especially for crystalline silicon, that's one single crystal. Okay. So the best efficiency, that's I'm not sure today's efficiency probably similar. About 10 years ago, about 20 or 21%, pretty decent efficiencies. Okay. And then that's in lab level. The commercialized level, you can make 15%. And then the market there, I don't know, market there about 10% at that time. Nowadays, not many people make this CICS software. So, but anyway, still this good technology you should. So, what is CICS, right? CICS means what? Best name is you have copper indium gallium sulfide. Okay, sometimes people use copper indium gallium sulfur. Okay? So, and then the device structure, you have the glass here, that's the glass, and then you have this MO as the what? The metal there, and then you have P-type, this layer type is main layer light absorption. Then you have N layer, that is the cadmium sulfide. That's similar to what? The cadmium sulfide is also used in the cadmium telluride, right? Then on top will be just hole transfer material, electron transfer material. Bottom will be hole transfer material. So if you look at the band structure, the same thing, okay? See, I have what? If you look at all the top here, or the top, you have aluminum doped zinc oxide or intrinsic zinc oxide. Then underneath you have this N-type, right? So that's what you see here, right? See this, this is a cadmium telluride, right? And then you have this zinc oxide, intrinsic, and then aluminum doped zinc oxide, okay? Then before that, this is N, right? This is P, this is P. And this, you form the p-n junctions here. That's the p-n junction. That's what we see. Because the CICS band gap is different than the cadmium sulfide. So that's why that junctions they are called heterojunctions. Okay. And the same thing, right? Because the electric field it goes more what from the P to the left. Potential, it's more like goes down there, goes down there. And the potential actually goes up, right? The electric field goes what? From the left to right, right? Electric field from left to right. Okay. Electric field is like this, right? Electric here. That's the electric field. Is this what the electric field looks? That's why these electrons will be pulled to the left side. The hole will be pulled to the right side. And then the band structure overall is something look like this. Band structure is look like look like this. Electron like this. Very efficient system, right? Under sunlight, you get electrons, electron or goes left, hole or goes right. You have the chat separations there. Okay. And then this basically is CICS, see here, this is from 0, from the top layer to what? To the junction, where the top level junction to what? To 0.5 micrometers. If you see, typically the CICS, you have like 3 or 4 micrometer CICS, right? You see from 0 to 3 is like that. So basically the junction happens or what? Or that regions. Or at these regions. Here. Look at this, typically, CICS solar cells. Junction happens basically in these regions. In these regions, okay. There you have what? You have this cadmium sulfide, you have this zinc oxide, intrinsic, and then also zinc oxide aluminum doped. Okay, that's it. Okay. So with that, I think that's about the heterojunctions, or also called symphony, symphony solar cells. Okay, symphony solar cell. And then I'm going to start a new chapter here. Okay, and new chapter what we're going to discuss is actually, let me close this and then. From the schedule, this is called light management. Okay, light management. Okay, let me share the screen. So light management. So basically, before we find a way to manage the light, we need to what? We need to think about what is the light, right? Especially in the lab, especially this morning, right? This morning or yesterday morning. I don't know if this morning or yesterday morning. You guys had what? You guys for your time, our time is morning, your time is evening, right? You guys had the lab tour, right? The demo for the light, for the solar cell testing. The solar cell testing, right? The student did not bring it to outside, right? Did not put the solar cell under the real sunlight. They put solar cell under something called solar simulator. Okay, solar simulator. So first, let's talk about solar simulator. Okay, you guys see the screen, right? Okay. So if you think about, look at the sun, right? Look at the sun. How can the sun give you the sunlight, right? Why the light come out of the sun, right? That's because what? Because the surface of the sun or inside the sun has a high temperature, right? The temperature for the sun, is about like 6,000 degree, 6,000 Kelvin, right? 6,000 Kelvin, that's about, 5,800, right? Celsius, okay? Because the sun is so hot, right? That it emit the light, right? Emit the light, right? So does that mean, now the question comes to you, the solar spectrum is something like that, right? This is solar spectrum is something like this. Spectrum is like that, okay? This is solar spectrum. Because the sun has a temperature, about 6,000 K, so the spectrum is like this, okay? Now let's see if I can, the sunlight also called white light. It's white light. It has many different frequency, many different color, right? Enclosed. Okay. Now let's see. The question come to you is that if I can have a object like this light bulb, right? If I can control my temperature to 6,000 K, right? 5,000 K, uh, I can also emit the white light, right? That white light may be different from the solar spectrum, but pretty close. If my temperature get very close to the temperature of the sun's surface, I will get the similar emissions. Okay, that's basically true, right? So that's come to something called black body radiation, right? So black body radiation means the radiation from anything can emit the radiation, right? If you think about you have computers there, right? Even your body, right? Your body radiate, right? Radiate infrared light because your body has temperature what? That's slightly higher than the room temperature, right? Maybe 10 degrees higher than room temperature. Since the environment, has a temperature lower than your body, that's why at night, people can use that infrared, right, sensor to sense you, right, to see you, right? Okay, that's okay. That means even the desk in your office, emit the radiation, but that radiation is only infrared radiation. Okay, anything has a temperature higher than absolute zero temperature will emit radiation, but that radiation goes to infrared. That's why we cannot see that radiation, right? Cannot see that radiation. So here, that's actually the theory about black body radiation. So sun is a black body because its temperature is high, so that's why it emits that kind of spectrum. If you have a light bulb, this light bulb, if you have same temperature as the sun, you can emit the similar spectrum from the sun. Okay, so this equation explains that. Okay, the difference will be this temperature. Okay, that's the temperature. Okay, and then at any given temperatures, if you want to figure out, which spectrum is the maximum, you just what? You just here. There's T here, right? T here, and then then when the T fix, that T fix, and then the spectrum is something like this, right? The spectrum will be something like this, right? In order to feel this lambda, right? This will be, can be intensity or can be, B will be photoflux, right? B will photoflux. You find what the peak wavelength, not peak wavelength, the peak light intensity, and what wavelength. You can basically just do what the first, derivative, right? You just do the first derivative with d and lambda. D, this guy with d lambda. You get that equal to 0, you find what's that what? What's that lambda? How to find lambda? This E here, that E is what? Equal to HC, C over lambda, right? Now this equation, you plug that to here. That's actually, have lambda included in that equation, okay? That can be, find out which lambda you have get what? You give you the highest energy density, the light density. The same thing, for solar spectrum is about 500 degree, 500 nanometers, right? About 500 nanometers. You can also use the black body, at that given temperature. This temperature is what? This temperature is how this in this equation. This equation, the temperature is at 6,000 K, and then this is a function of lambda. You can find out that peak to the to this this guy, you will find that lambda is about 500 nanometers. Okay, so with that, you can see, black body radiations is pretty clear now. The temperature determines the spectrum, right? The temperature determines, what is the radiation look like. That's why if you have temperature, it decreases from what? From 7,000 K to 3,000 K, you see the big wavelength gets to what? Longer wavelength, right? And then if this gets to what? If this gets to like room temperature, and then the peak will be moved here, move here, That's why this emit is room temperature. Everything emit what? Infrared light. Okay, so that's what is that about. That's the black body radiation. Basically, the temperature of this object determine what radiation, what frequency, what spectrons, what is the what is the distribution of that each different wavelengths, each different frequency, each different what bands. That's what is that about. So now they come back to the sun, right? The sun, because what? The sun has a lot of hydrogen inside. The hydrogen fusion, right, and then give you helium, right? That nuclear fusion process and then generate a lot of heat, right? That heat light up what? Light up the sun because too much energy is emitted, right? It's generated because this any mass loss or mass addition, right? That's its MC square, okay? That's why you get the temperature of the sun about 5,800 K, okay? 5,800 K. That's why the sun emits the solar spectrum like this, right? You know, uh, this is our Earth, right? And then here is the this is the Earth, right? And this is the atmosphere, this is the air, right? Then above the air, what you have space, right? The space, okay. In this region, typically we call that this kind of out space, extraterrestrial, you know. This is here. The dark one is space. If you measure the sun intensity in space, that's about 1353 watt per meter square. Okay. And then if you measure on the Earth surface, measure directly if the sun is here, sun is here. Directly the sunlight comes to the surface of the Earth. That's the sun already passed through the air, and then there's something called direct. The red one is that. The red one is that. It's called direct. Okay, direct sunlight, right? And then if you see here, on the surface, absorb, some sunlight comes directly from the sun. But there's some other sunlight, that has been come from the sun, but has been scattered, right? Because there's some scattering here, right? Here, then come to here. Now you have the sun, the light not only come direct from the sun, also from scattering. That's called global, okay? Global means direct sunlight plus some scattered sunlight from the environment, okay? That's why, space typically pretty high. That's like the black dark plot. The middle one, the blue one is the global, means we stay on the surface of Earth. We accept the direct sunlight. We also accept some sunlight scattered back to us by the atmosphere dust, right? And then the direct sunlight, that's the red, okay? That's the red, that's the lowest, okay? So that's what is this about? And then, since the atmosphere have many different molecules, right? You have this ozone, you have what? Water, oxygen, right? And then you have water, oxygen, you have carbon dioxide, right? You have carbon dioxide, right? Now you see, when you look at the solar spectrum, right? Outside the atmosphere, right? Pretty flat, pretty flat. Now suddenly, when you the when you measure the solar spectrum at the Earth surface, right? Because the sunlight passes through the air molecules. Air molecules have this carbon dioxide, has moisture, ozones that can absorb the sunlight, right? And then you see, whenever you absorption, you have gap, you have a dip, right? Deep, right? Deep, right? See all the deep, because there's gas molecules, in the atmosphere absorb this sunlight, okay? And then, especially, in the infrared regions, right? Look at the infrared region. The deep is huge, right? It's huge. What does that mean? That's why we learn about the carbon, right? See, now everybody talk about decarbonization. Why? Because the carbon dioxide in the air absorbs too much sunlight, right? If you have too much carbon dioxide in the air, they absorb that sunlight energy, and then during daytime, at night, they cannot emit that back to the space, back to the out space, and then the Earth becomes hotter because this carbon dioxide just keep adding energy, right, to the atmosphere, right? That's why our overall Earth temperature gets higher and higher. Okay, that's because of that carbon dioxide. Not only carbon dioxide, there's others like CH4, right? Methane is another one, right? That's also absorb a lot of sunlight and change that, especially in the infrared regions. Okay, so now we know that, right? The air in the atmosphere can absorb the sunlight, right? Now think about this way, okay? Because the Earth is pretty big, right? The Earth is pretty big, right? If you think about a person here on the Earth's surface, the Earth almost what? Almost flat, right? Almost flat. The atmosphere is also like pretty flat because we are so small, right? We are so small. If you stay here, the Earth almost flat, okay? Now let's talk about a long time, right? Long time. The sun is here. The sun is here. You see, right? See the sunlight passes through the atmosphere, the distance one. This one is O, this is where you see, this is B, right? Then, now let's see, at the evening, right? At the evening, now the sun goes to here, right? The sun comes to here, And then the sunlight passes through the atmosphere is what? OL, right? Now OBOL, which one is a longer distance, right? When the sunlight goes these directions to reach here, OA, and then the sunlight at noon reach, evening, the sunlight pass through too much what atmosphere. And then, as we just mentioned, the atmosphere, you have what? You have carbon dioxide, you have moisture, you have everything. You have also a lot of dust, right? A lot of dust in the air. So all this reflect light, absorb the sunlight, scatter sunlight. That's why as the sunlight passes through the air for longer distance, their intensity be reduced, more significant, right? So that's why we call this distance as air mass. Air mass, okay? Air mass. If you have more interaction with more, air, your air mass is higher, right? That's why even air mass higher. That's why the sun is the same sun, right? The light intensity goes out the same. But during noontime, we see we got a lot of sunlight. But during evening or morning, we see we don't get much sunlight because what? That's because atmosphere absorb it. Okay. That's why the definition here will be what? You think about the angle, right? The angle here is theta. That's theta. During daytime, the sunlight goes from in the morning, right? This is the morning 5, a.m., right? Then 6 a.m. and then sun just go return this direction. That's not the sun. Maybe I mean the Earth return too, right? So and then each of these angles, this angle theta, that defines the air mass. Okay, as the theta get what? Get 90 degrees, the air mass smaller. The theta at the beginning smaller, from 0, or 180, the theta is big, right? The theta is big, and then the air mass big. So the definition here is, air mass equal to OA divided by OB. Since OA always bigger than OB, right? So that's, if you think about this, this is what? 90 degrees. Just assume the Earth is flat, right? The Earth is not flat, but just assume it's flat. Then this one is OB, this 90 degree, that's why OA over OB, OB equal to what? That's basically equal to, because OB divided by OA is what? It's cosine theta, okay? Cosine theta. Now it's OA over OB is 1 over cosine theta, okay? Cosine theta. That theta is angle, right? So typically, for the, at different times during the day, the light intensity is different. So by average, right, you can average out, right? At different angles, you'll find out 41.8 degree. That's about the average, right? Each sunny day, by average, you will get that much sunlight, okay? That much sunlight. So that's why 1.5. Sometimes if you measure the solar cells in lab, you see, people always put that was measured under M1.5 because that's a typically a regular sunny days. It's not during what? It's not a noon time, but typically it's the average, okay? So that's about the air mass, okay? The air mass. So here's another plot. You can see, different time. In the morning, right, the sunlight, the air mass is huge, right? Right. And then the evening air mass is also huge, but the noontime air mass is one. It's one, okay? That's why the air mass is the smallest, right? In the noontime, that's why the light intensity is highest, okay? So that's just about the air mass, right? So the solar spectrum with air mass, and then as I just mentioned, outside this, the atmosphere, outside the air, the light intensity about 1353 watt per meter square. When it's pass through the atmosphere at noontime, you typically get about 1,000 watt per meter square. Okay, that watt per meter square, if you change to milliwatt per centimeter square, will be 100. Okay, 100. Okay, that's reduced. Okay, so here, the yellow one here, this yellow one is typical solar spectrum. And then if you think about silicon solar cells, the band gap is 1.1 eV. So that, you actually only, you only convert this much energy. I think we talked about this before, right? This, all this here is a thermalization loss, right? This called thermalization loss. Okay, that's basically, if this 1.12 EV, your light have 2.24 EV, then half of this, half of this just becomes thermalization. Real energy you get is this much, this band gap energy. Okay, that's what it means. Of course, these regions, because what? Because the band gap is 1.1. When your sunlight has some photons, that energy less than 1.1, they just pass through. They pass through the silicon wafers. Okay, that's infrared light. Okay, with that, I think it's clear now, right? It's clear that we can what? We can right? We can mimic sunlight. For example, if we use the Zan arc, right? The Zan arc, if I can, generate the arc that have temperature close to what? 5,700 degree and 5,700 Kelvin. So this one typically you get about, 5,700, 5,800, or 600, 6,000. They are all close, okay? And then it gives the spectrum pretty close. See the spectrum? This is sunlight one, and then this one is the sunlight at sea level, right? This is a sunlight above the, okay. See, when the sea level, that means on the Earth surface, right? The sunlight in the space, that's what, that's actually is what. See, the sunlight in space, that's what, there's no deep, right? But on the surface, see the deep, that's a deep, okay? And then the silicon is here, you can only absorb all these regions, right? All the regions. And then cut half what? Thermalization loss. That's why you only get this much energy around, okay? That's it. And then, when you have this Xenon lamp, that's basically, as the student show you in the lab, how the test sources, they turn the light simulator off, right? Light source on. And then if that's the, Xenon lamp, then the solid spectrum is something like this. You see some peak here. This peak typically applies the filter to get rid of that, okay? And then you can mimic sunlight, okay? You mimic sunlight. Here's some more information. Okay. Then, so here you can see is, M1.5 is the pink, right? The pink is M1.5. And then, the blue one here is the solar simulators, okay? The real M1.5 and solar simulator, you see their overall spectrum look very similar, but there's, details different, right? That's why you need to apply the filter to get rid of all the peaks, okay? The filter will help you get rid of peaks, and then help you, mimic, simulate what is this, to get something close to the sunlight, and then you can test your solar cells lab, okay? Typically, when you measure the solar cell in the lab, you have reference cells to make sure the, the efficiency is accurate. The reason is that, the sunlight, during even from the sun itself, it's not, it's kind of stable, but it's not that very stable, right? Because different days the sunlight is different, right? The same thing happens in solar simulator, right? There may be some temperature, there's some displacement. That's why the light, you cannot assume is always the same, okay? That's why each time you do measurement, you use reference cell because the reference cell work perfectly. And then use reference cell tell you what is sunlight really look like. That's why we have different reference cells, right? You have amorphous silicon, you have CICS, you have silicon. And then each of these, if you have solar cells that absorb the solar spectrum close to these three, you can use these guys as reference cells. But basically 3 reference cells, okay? There may be more. You can buy these reference cells. And then especially, if you want to test amorphous silicon disulfide polymer solar cells, you use 1133, okay, reference cells. If you work 6, cadmium telluride, cadmium telluride CD, okay, and then you use 1131-01. You use silicon that strength cells 1131-14. So that's about that. And then the next thing about the optical response of solar cells. When we talk about light management, we have to think about the optical response. Especially when the sunlight shines the solar cells, if there's quantum efficiency is 100%, you see one photon scatter 1 electrons, right? Then you see, you know, number of photons, number of electrons, you know, number of electrons, right? Over number of photons, right? Number of photons, right? And then that is the external quantity efficiency. If you consider some reflection, right, also transmission, you know, some reflection here R, right, some transmission here T. If you say total, you know, you don't consider that R and T. You only consider how much absorbed here, okay? How much absorbed here, okay? And then that will be what? QE, this one, EQE, that will be what? For the EQE, you can see EQE, that will be 5. Minus what? Divided by 1 minus R minus T. So basically, the denominator, you will not consider R, you will not consider T. You might subtract that, okay? And then what you get will be internal efficiency. Internal is only for the absorbed sunlight, you know, how much, you know, what is the percentage for that electron generated from the absorbed sunlight current external quantity efficiency. So here just shows a regular, you know, solar cell test by National Renewable Energy in, you know, Golden, Colorado. Okay, so this solar cell's efficiency is 4.33. It's not very high. Okay, not very high. And then the other thing, you know, typically when you measure you test the solar cell efficiency, especially in rare, they use normalized QE, normalized quantity efficiency, and then for the real one, there's a factor called K factor. K factor for different cells, different solar cell K is different. Right? If you have very efficient solar cell, K can be 100%. If you have very poor solar cells, that K factor can be, you know, 60%, 70%, or even 30%. Okay, that's how you measure this quantity efficiencies. Okay, and then so now let's see. Now let's you know, we understand what is sunlight look like, you know, also in the lab how you do the testing, right? And then now let's talk about the losses, right? The losses of this solar cells. Okay. So typically the losses. Think about the reflection, right? I think as I showed you, right? I think I showed you before the silicon wafer is very shiny, right? Very reflective. You can see your self image, right? You can see your face inside the what? Silicon wafer. That means it's too reflective, right? And then that's why the reflections loss about 30%. If you do not do the texture structures, so that reflection is huge. That's why you lost 30% of sunlight right away. Okay. That's why you need to do the texture structure. See, you want to add some also you can add anti-reflection layers. Okay. So what is the reflection look like? If you look at this guy, you know, this, you know, the sunlight is basically a wave, right? The sunlight is an electromagnetic wave, right? The wave goes through the surface because this is N1, N2. N1 is air, right? So equal to 1. The refractive index is 1. N2 silicon, right, is 3.1. You see, because the big difference between N1 and N2, right? And then there's reflections there. If this N1 and N2 get close to each other, you know, this is 2, this is 2, and then you have no reflection. Everything goes directly into the material. And you don't see the interface. That's what is reflection looks like. So typically when we talk about reflection, we talk about the refractive index. Okay. For that refractive index, typically we talk about is this, you know, the M, the real portion, There's also have one, you know, imaginary portion. So but because this N typically is much bigger than K, so that's why most of the time we use this the real portion N. Okay. And then think about here, you know, N is 5 here. Look, N is 5 for this wavelength. K is what? K is point maybe 0.2. 0.2. Especially the longer wavelength. The N is much bigger than K. That's why the imaginary part typically you don't consider. And then that epsilon is the complex, you know, permittivity of the materials, right? That materials were equal to N minus IK, okay? N minus IK. And then you can also see here for these equations, you know the absorption coefficient equal to 4 pi k divided by lambda, okay, divided by lambda. You see k is so small, but compared to lambda, k is big, right? Lambda is what? Lambda is what? 600 nanometers, right? Think about 600 nanometers, 600 times 10 power minus 9, right? That's what, right? 6 times 10 power minus 7 meters. So, okay, and then, you know, this is absorption coefficient. This is how the light will lose energy as it pass through. This is how much light, this is how much comes, and how much light go out. That's, as the distance is x, the outside outgoing light is always, you know, multiply the incoming light I9 multiply E minus alpha x. Okay, these are the common equations. You should be able to understand the question, the equation. Okay, that tell you absorption coefficient, also light intensity at different depths when the sunlight passes through the materials. So with that, here is the right. This one is the refractive index. N is bigger than I. I'm sorry. N is much bigger than K. That's the best you should know. Okay. Then think about silicon, right? Because silicon is a common material for photovoltaics. So silicon has absorption coefficient like this. At the low wavelength, the absorption coefficient is pretty high, 10 power 6, right? And then when it goes to what? Goes to here, 1000, get close to infrared, then reduce to 10 power 1. This 10 power 6, and then goes to 10 power 1. Cool, right? And then if you go to here, the 1400, now it's 10 power 1, minus 8, right? Now you see what? You see the silicon absorption coefficient very high at long at what? At short wavelengths, but very low at long wavelengths, right? And then you can see the absorption depth is just reverse, not reverse, inverse, okay? Inverse of alpha. If alpha is absorption coefficient, everything here divided by 1, and then you see this curve become what? Become something like this, right? See here it's like this. When you divide inverse, it's just opposite, right? Opposite. That's why the curve become like this, okay? That's what. That's the absorption depth, right? That's it. If my light intensity outgoing reduce, how fast it reduce. See the long wavelengths, they go very deeper into what? See the deeps, they go 10 power what? 6, right? Meters in the materials. Now here, the short wavelength goes 10 power minus 6 meters in the material. What does this mean? This 10 power minus 6 meters is what? Is 1 micrometer, right? See, this 300 nanometers photons can only pass through in silicon by 1 micrometers. But that 14, right? That 1400 nanometers photons can pass through the light, pass through in the materials, 1 millimeters, 1 millimeters. You see how that means, right? That's, how deep it can go into the fumes before they are fully absorbed, okay? That's called absorption depth, okay? Absorption depth, 1 over alpha, just opposite of the absorption coefficient. Okay? That's why, remember, when we discuss the p-n junctions, we see the short wavelength absorbed on the top, and then the long wavelength absorbed into this bark of this p-type silicon, right? And then there you can see, if this, you can measure this degree close to the, short wavelength, the typically and N plus or the emitter layer, right? When it's go long wavelength, go to the P layer, and then when it's go really longer wavelength, it goes to back contact. Okay, that's the same concept here. It's expand. Okay. So now let's see the this Franz layer reflection equation. That's a very common equation, right? The reflection equal to what? Equal to, if you see this n, this ns, then n minus ns divided by n plus ns square, right? Right, and then the transmission will be 1 minus that. That's the transmission, right? This transmission, that's the reflection, right? With that, you can do simply easily, right? If I know, if you see n over ns, right? Right, that's what typically, is the number, right? You assume if that from 0 increases, right, to 5 or 4, you see the reflection, happen like this, okay? When this equal to 1, it's 1, right? The refractive index here and here is the same. That basically is the light transport in the same materials, right? There's no reflection. That's why it's 0, right? 0, right? See here? It's 0, right? Whenever the difference, the delta n, ns minus n, it's not 0, either increases, it can be decreases to negative or increase to positive. And then the reflection gets huge, get much bigger, right? This R is 0.4 is 40%, 0.25, 25%. Okay, that's it. So the silicon wafer reflectivity rate, if you compare from what? This one, 300 is a 60% reflection. Then visible light, somewhere from here, so able to see from 400 to 700. The average is about what? Average here, right? About 35%, right? That's 30%. because overall, if you think about visible region about 35%, because between 32% to what to about 45%. Okay, so it's huge reflections for the silicon wafer. Okay, so here just shows this I think something you guys known before, right? The reflection also related to the p-type polarization or s-type polarization. Okay, so typically it will be equal to what? If you think about here, you know, this N9, this NS, N9 is air, NS will be sample, right? This can be different materials, can be all air and water, right? That can be sand, any liquid, right? And the N9 multiply psi theta 0 equal to what? NS psi theta s. This one is not reflection is here. This one is called what? Refraction, right? Okay. So typically the sunlight, because sunlight has all directions, right? You can see, overall, is it here? What is this? The sunlight can be equal mixture of P and S, right? P and S. You can see P and S polarization. P basically will, if it's out this paper, P will be what? Parallel with paper. And then the S will be what? It will be like perpendicular. Okay. That together can be 1. So that R can be what? Can be the half. Okay. Each of that take half. Okay. So here shows the shows the angle, right? Because if you look at here, the reason here this angle matters. The angle matters. Okay, this angle matters. This matter. The angle determine finally the reflection. Reflection is related to the angles, right? So here, as the angle change, incident angle change, you can see this is for RS, right? But RS is remember RS is S is a S polarization, right? S polarization, S polarization. This is P polarization. Okay, P polarization. You see, S polarization as angle increases, the reflection increases, right? And then the p-type is actually reduces to something, right? About 60 to 70 degree reduces and then increase again, okay? This one is basically the light goes from the smaller refractive index to bigger refractive index, okay? See the interface here goes from there to here. Now, if your light goes from larger refractive index to a small index effect, it go up, you will see something interesting. There's something called total internal reflection. The light will be trapped inside. That's the optical fiber, right? The optical fiber, the light transport in the fiber, light cannot get out. Why? Because the optic fiber, the inside, their reflecting index, the made engineer the way the inner is bigger than the outer, right? That's how that when the light tries to go from the higher index refracting index to lower refracting index at certain angle about here 30 degrees, that's you will see a critical angle. At that critical angle you have total internal reflection. The light just trapped inside. Okay, trapped inside. So that's so now come to the question, with this much information, how can I know, how can I reduce my reflection? That's basically, if you reduce reflection, basically you add what? You add a layer of materials here. That reflective index will be between N1. And between, this N1 should be larger than N9, but smaller than NS, right? And then since this reflective index in between, help reduce the difference between N9 and N0 and 1, also between N1 and NS. That's why you reduce the entire reflections, right? Because the difference between N0 and S determines the total reflection. Now you add some materials in between. They have the refractive index just between them. And then the interface refractive less, this refractive less. That's why overall you can reduce reflections, right? And then that's also whenever you deposit anti-reflective layer, you just choose the materials, their refractive index is between them, right? You put on top, that's it. So simple, right? Very simple, okay? So with that, you can see with that, the minimum, reflections you can give would be N0, NS minus N0 square, right? Then divided by that, N0, NS plus N1 square, okay? First, it's their difference, right? And then take a, square, and then divided by their sum and then their square. Okay, that's so. Now let's see if my air is 1, my silicon is 3.5. I deposit materials in between zinc oxide. That's refractive index is here. This one is 2, right? If this is 2, I plug to the equation, right? 3.5, right? Multiply 1, right? That's 3.5. And then minus and 1 square, that's 4, right? And then the bottom is 3.5 multiply 1, and then plus, that's and 1 square. You get here only 0.4%, right? Initially, if this, 30% reflection, now reduced to 0.04, right? So now you see that you just choose the right materials that has the refractive index between N1 and S. You can make this anti-reflection, okay? Anti-reflection. So here's a survey here. It shows that, when the light travels in a medium, what change, right? Typically the light, when the light transfers in the medium, you know what? The speed reduce, right? Speed reduce. And also the wavelength reduce, okay? It's 1/4, right? But the frequency of the light doesn't change, right? And also what? The period will not change. The period will not change, okay? Period will not change. That's basically this light transport in the what? The frequency doesn't change, the energy doesn't change, right? The light transport what in the, the air or in the material, their energy will be the same, unless they are absorbed by the, by the band gap. Their energy lost directly to the electron. Otherwise, they don't change their frequency. Okay. So this explains that. I'm not going to talk about that. So next, something else I would like to plan. Whenever you're at, I think only we talk about N1. So another reason, when you have this N1, you also care about, how thick the N1, right? How thick the N1. Basically, what you see here, the light comes here, the first refraction happens here, the second refraction happens here. Now there's real one and real two, right? Real two travel, longer distance, right? Because it goes to here and here, right? Now, if you add this and add that, right? Now this real one, real two, or what? You can modify them by the cyclics. So make them, they are in phase or out of phase, right? This one in phase means what? Is the peak from real one is the, corresponds the peak from the real two, right? And then we call this in phase, right? And then for this, reflection what is high, right? Because now it's a very high reflection, right? Now let's see if I can modify the cyclics to make sure the peak is valley, right? The peak is valley. The valley is the peak, right? To add this together, you cancel each other. Now, since this real one, real two cancel each other, there's no light come out. And then you have what? Zero reflections, right? Zero reflection. So for that point of view, the D matters, right? D matters. So basically, this one plus this, the distance, if that is equal to what? Is AB plus what? Plus BC, right? Plus BC is equal what? Equal the, you would see that would be, lambda, right? M lambda, right? M lambda. And then you know what? And then since when this has N1, and right, and then this what? The lambda will be what? I think, yeah, the lambda will be multiplied here, right? Because the speed, right? The speed is lower, right? Speed lower, in other words, means what? Wavelength is longer, right? And then the add up, right? That's a big reflection, right? If this is equal to 2m, right? Oh, m plus half, right? Not 2m. It will be, if that's m plus half, right? M plus half lambda. And then their phase will be just what? Out of phase. They cancel each other. There's no reflections, okay? So the minimum will be what? The minimum, oh, there's AD here. There's AD here. This plus that minus AD, okay? Minus AD, the AD. Use this one. Here will be minus AD, okay? AD in the air, so you don't multiply that N1. This and this, okay? Since here there's no reflection, then the minimum thickness will be m equal to what? M equal to 0, right? M this equal to half, right? For there, you can see, you can calculate, this m is what? 0. You get 2 what? 2 and 1 d equal to half lambda, right? And then d equal to what? D equal to lambda over what? 4 and 1. Okay, 4 and 1. That's the thickness. Typically, someone, if you ask someone to deposit the film for you, that's the CICS you will ask him to deposit for you. With that CICS, lambda divided by 4 and 1, you get 0 reflections. Okay, 0 reflections. So that's about that. Okay, here this just it just shows that how that works, right? Okay. With that, and then question asks you, is the refraction loss a serious issue for organic solar cells? Typically, it's not, because you talk about silicon, right? This and 0 is 1, and 1 is what? 3.5, right? But for this, for silicon, okay, silicon. Organic, right? Organic, typically this organic N1 is like 1.5, N1 is what? N1 is air, right? N1 is 0. See, the distance is different, right? The distance here is 2.5, the not different distance. The difference, the delta N, right? Here's bigger, no, than the delta N here, okay? When the delta N is not that big, you don't have much reflections, okay? That's about that. So that's why, in organic, you have like 4%, right? That's not a big deal, okay? The next thing about why, texture structure can reduce the reflection. You think about this, the sunlight comes here, and then the first reaction here, right? Then you get what? You get that reflection R1I, right? This R1I, right? And then to the second reflection is the R1 R2I, right? This R1 R2I, right? See, if you assume this R1 R2 is the same, right? That R1, that's equal to 0.3, 0.3, and then R1 R2I, that reflection here, is what equal 0.9, right? I. See, because -3 multiplied by -3 become -0.9, right? That reflection is reduced, right? If you don't know texture structure, there's 30%. Now you have texture structure because reflect again. That how much reflect will be only, 30% of that, reflected part. That's why it's only 9%, 9%, right? That's 9%, okay? So you can also understand this way. Since I have silicon, half air, right? Silicon 3.5, right? Air is 1. So I can see average will be what? Like 1 plus 3.5 divided by 2. So the overall, this layer, there is what? There will be like 0.25, right? 2.25, right? And then now this 1, now it's 1 and 2.25 instead of 1, 3.5, right? That's how you consider that, the texture structure reduce reflections, okay? So here's just different, structures here, You have nanowire, you have nanorod, you have nanopinel, many structures you can use as the texture structures. With that, I believe that's the last slide, okay? I know today I'd like to take a few more minutes, okay? So any question from you guys? If not, tomorrow will be the last lectures, okay? Tomorrow we're going to talk about the loss mechanisms, okay?
Yes, participants, if anybody is having any question, they can raise their hand, or else you can ask tomorrow, because we'll be having session tomorrow also. I mean, tomorrow in US time, obviously.
Yeah. So you guys will be evening, right? Yeah.
Yes, sir. Sir, I guess we don't have any question.
Okay. Okay, so tomorrow is the last lecture. We're going to discuss the loss mechanisms, right? We'll figure out, what kind of loss is, how to deal with these losses, okay? And then if not, I think I have good evening, good morning, right? Have good morning for you guys, okay?
Yes,
Good
sir.
weekend
Yes, sir.
too. See you tomorrow, okay?
Okay, okay, sir. Thank you, sir.
Okay, no problem. Bye bye. Yeah.